Hi everyone, this is Advanced Statistics for the Social Sciences. In this lecture, I'll describe the characteristics of sampling distributions. In the last lecture, I described how to create a sampling distribution. Now I'll discuss each of these characteristics of the sampling distribution. When referring to these characteristics of a distribution, they are sometimes called moments. The first moment is the measure of central tendency, for example, the mean of the distribution. The second moment is the measure of variability, for example, the variance or standard deviation of the distribution. The third moment is skewness. Skewness is a departure from symmetry. Negative skewness is where the tail points to the low scores, the pink figure. Positive skewness is where the tail points to the high scores. That's the blue figure. The fourth moment is a measure of kurtosis. This is being more peaked or more flat-topped relative to the normal distribution. The shape of the blue distribution is platykurtic. I like to remember platykurtic by thinking that plat rhymes with flat. The platykurtic distribution is flatter. Kurtosis that's similar to the normal distribution is called mesokurtic. So if a distribution approximates a normal bell curve, it's mesokurtic. If its peak is very sharp and it's more narrow and taller, that's called leptokurtic. That's like the red curve in the figure on the left. Let's discuss the central tendency of sampling distributions. The mean of a theoretical sampling distribution of the means, the one that comes from the mathematic proof in which all possible samples are represented, is represented by the Greek letter mu, which symbolizes the population mean, with a subscript of x bar, which represents sample means. We are taking the mean of the sample means in the theoretical distribution. The mean of an empirical sampling distribution of the means, the one that comes from actually resampling and plotting the means, is represented by x bar with a subscript of x bar to represent the sample mean of the sample means. This is because we're actually computing a large number of means and then taking the mean of those means in the sampling distribution. The mean of the theoretical sampling distribution of the means will equal the actual mean in the population. This property is related to what we talked about in the previous lecture. The mean of the empirical sampling distribution of the means will not be exactly equal to the actual mean in the population. Let's talk about the shape of a sampling distribution. This is important, so pay close attention. Something to remember here is that n is the number of people in each sample for which a mean is computed. As the sample size or number of cases of your samples increase, the shape of the sampling distribution of means will approach the shape of a normal distribution. If you are taking a bunch of samples that each have 2 people in them, the sampling distribution of the means does not look very normal. The means are all over the place. It's platykurtic. If you are taking a bunch of samples with 4 people in each of them, the sampling distribution of the means is looking a bit more normal. If you are taking a bunch of samples with 8 people in each of them, the sampling distribution of the means is looking even more normal. This is true regardless of whether the shape of the raw scores in a distribution is skewed or symmetrical. Remember, these are means from those original distributions of raw scores. The technical name for this phenomenon is the central limit theorem. The central limit theorem is a mathematical theorem that states that as sample size increases, the sampling distribution of the mean approaches a normal distribution. Another way to think about this is that regardless of the distribution of scores in a population, the sampling distribution of sample means selected at random from that population will approach the shape of a normal distribution as the number of samples in the sampling distribution increases. So think about this as the number of people in each sample, not the number of samples taken. We're talking about taking an infinite number of samples either way. Here's another figure that demonstrates the central limit theorem. Note that with n equals 1, that is one person in each sample, a lot of different means were obtained. So essentially each sample had a different mean. With n equals 10 people in each sample, that's on the bottom of the figure, more samples had the same means. We're getting the same or at least similar means in many samples. As n is increasing, the shape of the sampling distribution of the mean is getting more normal. You can find many YouTube videos about the central limit theorem that provide a more in-depth account of the theorem. I've provided 2 at the bottom of this slide. I said that regardless of the shape of the distribution for the raw scores in the population, the sampling distribution will approach normality with increasing sample size. But how big does the sample size need to be? Well, it depends on the shape of your raw distribution. For example, if the population distribution isn't normally distributed, but it is unimodal and symmetrical, then an n of 5 or 10 may be sufficient. And if it is not heavily skewed, then n of around 30 people in each sample, as you're creating the sampling distribution, is probably enough for the sampling distribution of means to approach normality. If the population distribution is bell-shaped, then the sampling distribution is bell-shaped for most sample sizes. When a population distribution is more skewed, it requires larger sample sizes, but usually not more than 30. In practice, for random sampling, the sampling distribution is nearly always approximately bell-shaped. So we've discussed the central tendency and the shape of the sampling distribution. Now we'll move on to variability of the sampling distribution. The primary concept that pertains to variability of the sampling distribution is sampling error. Sampling error is the amount by which a sample mean differs from the population mean. Sampling error is a big deal because it's important to know if your estimate is a little off or if it's really off. Having low sampling error means your estimate is pretty accurate. You can think of sampling error as a deviation. Sampling error is equal to x bar minus mu. The deviation represents how far off a sample mean is from the population mean. Let's consider an example using the amount of times students study per week in college. If the actual mean hours per week studying in the entire population of undergrads is 8 hours per week, and I got myself a sample of undergrads and found that their mean hours of studying per week was 8 hours, the sampling error is 0. 8 minus 8 equals 0. I would have no sampling error. However, if the actual population mean was still 8 hours per week, and I took another sample of undergraduates and found that their mean hours studying per week was 5 hours, the sampling error is -3. I would have a deviation of -3 hours, meaning that my sample's mean was 3 hours lower than the population mean. My sample may have had a mean that was 3 hours below the population mean for hours studying per week for a variety of reasons. It could be due to low sample size, random chance, using a sample from a non-competitive college where students just study on average less, or any number of other reasons. The standard error of the mean is a way to characterize the sampling error. The standard error of the mean is the standard deviation of the sampling distribution of means. The standard error of the mean is calculated by dividing the standard deviation of the population by the square root of the size of the sample we theoretically drew from the distribution, from the population. We already talked about standard deviations of a distribution of a sample's raw scores, so this shouldn't be a totally foreign concept. We're now just talking about means rather than raw scores in a sampling distribution. That's why we have the X bar subscript on the sigma, which symbolizes standard deviation here, to differentiate this standard deviation of means from standard deviations computed on scores in a single population distribution. The larger your N, the lower your standard deviation of the sampling distribution. For the sampling distribution of the means, this is the standard error of the mean. This makes sense given the central limit theorem. This concludes part 2 of types of errors and distributions. In the next lecture, I'll describe the characteristics of estimators and how to use z-scores.